Okay. So, I mean, I have to, admit, so this is kind of, I just got the slides composed and my work is kind of in progress, but I really first make acknowledgement to Worf and Robert. Thank you so much. I saw for the many insightful discussions. So you helped me actually to solve my specific problem. So I'm talking about how I use this universal small manufacturing reference model to develop a reference model for additive manufacturing model predictive control in part quality management. So basically, the model provides a guideline or framework to analyze model predictive control for AM and also to use to synthesize appropriate one with the right configuration fit for your purpose of your applications or based on your organization's limitation. Okay, so myself, I have been working with many colleagues through the years, but last few years since COVID, I'm pretty much very focusing on additive manufacturing control and try to make a data management, data integration, data fusion, and methods and schemas, data models, as well as analysis to enable that, like a data registration, data fusion. Okay, this is in that scope. So to have one specific area to do part quality control based on the process control, because currently additive manufacturing process, the loop is not closed, it's purely open loop. That caused a lot of quality concerns, but also the constraint of the qualification, which is regulatory right now for aerospace or medical area. So it doesn't allow open loop control, but from research, we try to investigate. So how can we prove the closed loop control supersedes the open loop control and how that can essentially be built into the standards for regulatory standards for qualification. At the same time, we are able to provide a standard guidance. So either within ASTM or John with ISO, which is TC261. So I'm working with. Okay, that's the context of my project. And I just, a little bit overview of the additive manufacturing. This shows actually, this whole process shows it's more like a SLM process. People, you also say laser powder bed fusion process. So you start.
Please. Yeah, can you put your presentation in presentation mode, perhaps?
Okay,
we
sure.
See all your slides.
Okay, you cannot see well. Okay, let me see.
Yeah, okay. Now we can see the presentation.
Okay. Just so yeah, the left side shows the process, the physics of the process. So with a procedure of coating the powder bed, a thin layer of powder bed, then you expose the material by melt them and solidification into the solid state with a shape which is specified by a CAD model. Okay, this is the whole process. How you build this layer by layer, you repeat this process. And yeah, I'm not going to talk about the advantages. People predict this value start slide off, we don't know. But there are some challenges, right? So we are facing the basic quality issue. If I've seen that, right, the successful rate is very low. So those are a lot of failure reasons. And also even you build, SIM successfully. So you have seen the part quality issue. So lack of fusion, can see that, and also some of the microstructure undesirable. So this will cause the part fail, fatigue, fracture or corrosion. So these are highly, critical for the aerospace or medical FDA, regulated area. And that's a reason. So they are very strict with qualification. And then also the cost to produce the parts are very expensive. Okay, so that's what we see that, how can we improve that? Basically, we need to do both process understanding and quality control. So process understanding, so I just dissect the information of AM built into, we give the process inputs, we can monitor the process. So the inputs are the scan strategy, and these are energy density. So when we scan, how much we apply. Other information like material characteristic, the particle or for powder bed fusion, the powder size distribution, then the design. Sometimes your design is not achievable, right? So that's the same thing with traditional manufacturing. And what kind of machine use? Each machine has their own capability limit. Then when we start build, so we monitor the process, we install sensors, we retrieve observations. There's a lot of configuration of the observations and the sensor installation. And we also need to do data process to obtain the signatures, because each of them, modality of sensing, they kind of, it's just a symptom, right? So you need to derive the meaning out of them. Okay, this is just to show some examples. We do melt pool, then we can, register the melt pool observation on the build layers. Then we also can do statistics, see, the melt pool distribution. Those are all we call signatures, right? So our hope is, in the future, right now, the regulation regulates, you have to fix your process inputs. So if you define the scan pattern, the process parameters, and you perform multiple builds, prove, okay, you can get good qualified parts, then you have to stick to it. You freeze this setting, then you will continue to build the second article, third article. So right now, if we are able to, monitor this and we find the signatures, so they are kind of define the quality. Basically, we will see that the signatures are determine the structure, microstructure, and the structure determine the final performance, like density, strength, fatigue, performance, corrosion performance, right? So essentially, we want to control. We want to basically put the control limit on our signatures. Then we will do the similar thing with traditional manufacturing of statistic process control, right? So, but to maintain the signatures within the control limit, we have to apply feedback loop control. So this shows, we have spent so many years trying to understand this relationship only with the models identified to correlate from, the bottom to the up. We are able to do the decision making or control, right? This is our feedback loop control. Okay, so yeah, this is example. So I'm just to show a little bit, the process monitoring control methods, really multimodality, right? We have layer-wise image. You finish a layer, you take an image. Then you have, the layer-wise image, like exposure layer. So this is exposure layer. You also have powder bed, which is like you recode a layer, then you take an image. So usually used to detect the defects in recoding. So then you have melt pool monitoring that shows that this is coaxial. So basically the laser path and the optical path are the co-located for the camera and the laser. Pyrometer is temperature measurements, and the process settings, we apply process parameter. We also can read back using like encoder to read the position, etc. And some of the other things like acoustic. So this shows more like acoustic, these are the process settings and the energy. Okay, let's just show you, for in order to do process control, what are the observations currently we have. Okay, so now go back to, we have done some optimization. So this is an open loop, right? So we originally designed a control strategy. So based on simulation, our understanding, really shallow understanding, then, it doesn't work well if you see that that we observe the process signatures melt pool. You will see that the melt pool, okay, area, this is the signature of the melt pool area. So it really goes up in the middle because the pattern we have is called the spiral pattern. So you can see that the energy will concentrate finally. So because you accumulated the initial heat, right? So you cause huge melt pool size at the beginning. So you can see that. So this is the distribution of that. This is just a quantitative measurement. So it shows how melt pool will look different at the D. So you will see melt pool is huge. A is more regular. A, B, C gets larger, right? So that, turns out to the the distribution. Okay, so then then we try to apply optimal scan strategy. So what happened is, instead of apply strategy like this, you have concentrate heat in the middle. So we actually cool down, we apply less laser. So then we will see that the melt pool distribution will be much different, right? So the peak, reduced. So, okay, then the melt pool looks more normal, right? So just by visualization. So then let's take a look at, so those are the, the change of the peak. So then we will see that this is the open loop process optimization. So originally it's like this, after optimization is like this. So much, much better of service. This does see that how the relevancy of the process parameters to the process signature melt pool to the final property. This demonstrates that if we control melt pool, we are able to control the final performance of property. Okay. So, however, the feed-forward control we just see is not sufficient, right? You see that, right? Still little peaks here, and we'll still see the defects in the middle, and some other surface areas not good. If this area, basically we'll see somewhat this area. Okay. So feed-forward control is not sufficient. So we want to close the loop, right? Basically, we have pre-programmed scan parameter. That's fine. We still put there, but we monitor the process, we measure the process. Then we do real-time control and optimization. Then we update the process parameters. It's this, updating policy can be very general. Okay, like from layer-wise, you repatch or you rescan, or within a layer from pattern to pattern, from patch to patch, you can do update, etc. Right? So everything, we still need to do engineering phase of office offline modeling. So now let's look into the model predictive control. It's one type of feedback loop control. Just give you general idea about it's model-based first, right? Then second, they will do based on the current measurement. It's like round robin of a PLC loop, right? It's not PLC, it's just like the object block, function block. So you get a measurements, for example, melt pool, then you product the prediction. So based on your predefined control, okay, so you can predict what the new melt pool will look like and how the new melt pool will relate it to your property, like defects. Then you build it into the object function, like to minimize defects. And you put the constraints on, like the laser cannot be, because my laser is from 0 to 500 power watts. I cannot go beyond that. And also I cannot change that fast. My changing time is 50 microsecond for laser. Those are the constraints I need to use. Then I will solve the optimization problem. So I'm going to optimize for a horizon of the future prediction of the defects, for example. Then you only apply the first control, like the laser power. Then you repeat. This is the traditional model predictive control. So if you see that there's a flat structure, the component including, you need to have a state representation. You need to have an observation model. Then you need to have an optimizer. Then you need to create a control strategy. You have to use a model. Okay, these are the critical component. So when we design this apply MPC to AM, we have to identify all those components. But in the AM domain, okay, I need to make this fast. There's some challenges because AM model predictive control itself is an advanced control strategy, has to be was standardized partially in the process control, like 15746 defines some information model or modules for advanced predictive control. But those just show you some of the community lag guideline on developing the MPC system for part quality control. It's a high level goal. That's the reason I want to make a reference model. Now back to the relevancy to this universal smart manufacturing reference model. This is somewhat similar to robots, but you might see the relationship is based on my understanding. I was deeply involved with the first technical report of universal smart manufacturing reference model and a little bit of 36339. So then I, kind of step out. So this is based on my understanding. So first, the universal smart manufacturing reference model is a specification. So specify how to make a smart manufacturing reference model. So the relationship SMRM has to conform to USMRM. So based on the specification USMRM, so we construct this kind of, I would say this class model, data model for SMRM. It has to have aspects. These are all concepts. It has to have dimensions. It has to have, not has to, but optional has facets. And so the SMRM is driven by a modeling purpose, and this modeling purpose comes from stakeholders' concerns, okay? So these are the relationship, and the modeling purpose define what are the facets we care. Then the relationship between aspects to dimensions, so it's composed of dimensions composed of them, but based on coherence rules. Similarly, so facets is a combination of dimensions, so based on defined interactions, necessary interactions of facets. And the facet, when we define the facets, because of the address stakeholders' concerns, actually is in a certain context of the business process. Now we move to the semantic part, right? How we identify dimensions, aspects. So these are the, the tremendous work Robot has been working on, trying to formalize this systematic approach. So how to identify aspects and dimensions, so comes from your semantic models. So my understanding is traditional, my feeling is dimensions comes from the concepts we define in concept system, and aspects is defined by conceptual domains, usually is enumerative domains, right? So, but both of the conceptual domains and concepts are included in concept systems. So I give example of a concept system. The one we have developed is called AM, Common Data Model Ontology. So this shows its instance. This shows is the type, right? So that's the reason I use relationship instantialize, okay? So this ontology we are working on, we also have control ontology. It's not really that formal ontology. 15746 is about control. So it's also a concept system because it's bringing all those definitions of the control terms for a process control. In addition, I also look into some reference of sensor ontology. It's also a concept system like SOSA is sensing, observation, sampling, and actuation ontology. So these are instantialized this, okay? This is a class, these are instance. So now back to this. So we have, we identify the concepts. We are now ready to build a reference model for AM model predictive control. So I separate a domain specific one and a separate domain from the technology specific. So the left side is called AM reference model. So it is an instance of smart manufacturing reference model because it's going to have dimension. I have to assign dimensions. I have to assign aspects. So I will show you later. And the right side is model predictive control reference model. It's technology specific reference model. So it's an instance of SMRM as I defined here with all the, all these components and associate concepts. So finally, there's one thing we probably can think of the usage is like a reference model can be composed by multiple reference models, right? So here, I finally make AMMPC reference model. So it's an instance of smart manufacturing reference model. So, but it's kind of composed by domain-specific reference model and a technology-specific reference model. Now I created this reference model. Now I'm going to, based on this reference model, to develop my specific implementation model or architecture. So basically what I did two things. One is, I try to using the reference model to develop information model. I put the conforms to, it's very similar to this conforms. Some I also think it be reference to because it's not really semantically very well defined about I check on dictionary about it. So basically, reference model and model, their relationship, reference to guideline, etc. But I use conform to, just generally to data. This information model reference to the dimensions aspects we define in the reference model. Similarly, I also make a specific architecture for one of the case. The system I'm developing also conforms to this reference model. So the information model here, so basically it's represented, based on specification of UML, which is a meta model. And this information model is a logic model. Based on this, I develop AM data schema. This schema is conform to this inference model. And this data schema actually is used to structure the data set, data system, in the data system. Okay, I'm going to use ultimately to validate the performance of this model predictive control for one of my system. So which is based on the specification. This specification ultimately can go back to the stakeholders' concerns, right? So essentially all the modeling purpose. I didn't draw the link because it's kind of make that too complicated. Now I'm going to talk a little bit about all these colored blocks I developed. So I assume not everyone agree on this, but Wolf and Robert talk about all the top part about how URMSM or SMRM can be used. So I'm talking about my case, okay, a little bit. So now I just go to a simplified AM process reference model and conceptual domains, okay? So we have a lot of other concepts. My concepts only focusing on process, okay, AM process. I have process parameters, can control the process state. And I have process observation, can observe process state, right? Process states have type, okay? So what type of the process? We just like types of process signatures or types of the state. And also the process state can be represented at different scale. So now I define all these conceptual domains, so which is in AM, or especially for laser power diffusion. Process parameters can be laser power, beam size, scan speed, hatch distance, layer thickness. I just put it's not inclusive, right? Just example. Process state type can be temperature, flow rate, cooling rate, remelting of the material at the scale we identified, right? So the scale, so we can represent the state at a specific small voxel, we call it point. Also track the complete track when we scan, or the complete layer. After we finish that layer, we have the process state of the layer, or the part is so the 3D accumulation by far. That's my process. So those are the conceptual domains I defined. And so we are in the middle of standardize this, okay, to make us a formal conceptual domains. Then look into the process observation. This is really laser powder bed fusion. So the conceptual domains can be coaxial Melpool image, coaxial pyrometer, acoustic, or layer-wise. So when these are not ordinal, if you look at this, right, these are ordinal. You start with small scale, you go up to the macro scale. This is also, there's no order here. There's no order here. So basically those conceptual domains, not all of them have any coherence rule except this one. So that's what I feel, coherence rule could be optional. Anyway, so I summarize this and I create a MPC related AM process reference model. I only have 3 dimensions, right? Actually, I could have 4, right? So yeah, I need to have another one because I process variable. I make a 1 dimension. Actually, can be separate in 2. So here I have 4 dimensions of concerns, okay? And each dimension has all these aspects. Those are defined by my conceptual model, okay? These are concepts defined in my concept system. These are conceptual domains defined in my concept system. So combine this, create this reference model to represent the AM process. Now move to model predictive control reference model. It's a little bit more complicated, right? So we just show you that how the model predictive control, the component, right? Just now we show that we need to have a state transition model. We need to have an observation model. We need to have objective function. Then we have to implement optimizer, and we create a control. We need constraints. Then we create a control strategy for implementation. So now that's my reference model. Okay, I have 1, 2, 3, 4, 5 dimensions. You can see that relationship, right? So I need to have a predictive models. This product model define the dependency between control states and between observation of states, right? And I need an optimizer, so it has the input of object function constraints and also predict models to generate the control. And the optimizer will be implemented on a computing infrastructure. So then optimizer use search sum solvers to solve that thing. So those are the 5, concepts I kind of feel are critical for choose or configure with the conceptual domains, right? Like model type, this is something very interesting today because traditionally we all use analytical model for MPC. Now we have to include numeric model simulation based, for example, and machine learning models, which are not a black box models, okay? But, the progress of, hybrid model could embed a physics meaning in the machine learning model. This is very important area for our research, right? How things changed, computation requirements, as well as, the performance, right? So then my objective could be lack of fusion index, keyhole index. These are all porosity or bonding effect, surface performance, density, geometry deviation, strength, etc. Okay, these are the conceptual domains, right? And for computation infrastructure, I could implement things in FPGA or edge computing or fog computing or cloud computing. The solver could be LGQ, Bayesian, or genetic algorithm. These are just the examples. And the prediction zone could be N layers or N tracks or N control intervals. Okay, those are the 5 dimensions. I kind of feel we need to guide the user to pick which aspect. Okay. So essentially, I didn't choose all the dimensions. I selectively choose the dimension for my AM MPC reference. Those are dimensions I need to concern about. And also those are the aspects are the options I can choose my MPC configurations, okay? At which layer I do this. But sometimes when they interact with each other, for example, the scale of the material state for prediction or observation. So it matters what computation power you have. So for really voxel level, because we're talking about every 10 microsecond or 100 microsecond, even track level is every few a millisecond. The only thing I can do the computation will be probably especially if we use machine learning model, will be have to be FPGA level, but we're not sure. That's some research we are doing. Can we implement CNN in FPGA? Do we have typically enough flip-flops to do that complicated algorithms? And we have part of other research is to simplify CNN to reduce like a weight to 0 and a 1. And we check the performance degradation at the same time, computation requirements dramatically reduced. Okay, those are, also define the research area. We can do the interacts of different aspects, and also use what kind of observations matters, right? The multiple images optical definitely is 120 by 120 dimension every, our case is 100 microsecond, we generate that part of data. So that, also limits, where can I do this implementation and what kind of models I can use, right? So those are, just overall the reference model developed from this USMIM. So I just to show you some other ontology I use, like sensing when we try to create taxonomy or conceptual domain for the observations, like SOSA is one. This AM ontology we are developing to show, the domains, the subdomains. This shows multi-scale AM physics matters what kind of observations we should care because essentially it's a feature of interest. So just quickly, this just show you, that we can do state at different scale. So individual grids, voxel level and track level or layer wise, so or part wise. So this just shows, just more details about how to create a predictive model, state transition, observation, and how optimizer works. So now this is useful. The reference model I found, it's first useful for me to analyze my peer work, right? I did a lot of literature review. This one from Journal of Manufacturing System, they claim they make an MPC. Then I look into their implementation. Actually, I can annotate which aspect their MPC. They do point-wise control. They have point-wise, of implementation. They observe the temperature of the voxel, and they also they using the objective is above, cooling, melting temperature, using Bayesian for the predictive model. So the observation models, they also use LSTM. The prediction zone is 1, and they use objective is porosity and implement it in FPGA. This is I made up because I know they do everything in simulation. So another one is also, I did the same thing. I use this reference model to analyze. Then I can compare work, right? So the most important thing is I use that for MPC design for NIST AM methodology testbed. If you take a look, it's different from commercial system because we have a lot of freedom. We can really assign the laser power of every 10 microsecond directly to the Galvo control, okay, the Galvo system. And for observation, we have a steering camera. Okay, we have a layer-wise camera to look at the layer, powder coating, and exposure. We also have high-frequency 10 kilohertz Melpool image system. So those are the two, and also I have encoders. I can have the data acquisition system to get the real position. But this shows the architecture for the hardware. So you see that we use National Instrument FPGA for data acquisition of the Melpool images. We use another FPGA to do the control of the Galvo. So which says kind of I'm able to implement something in the FPGA. So then, when I start to...
Okay. So sorry for interrupting, but just 1 minute for wrap up so we have time for questions. Thank you. Okay. Thank you.
That's it. Yeah, that's about, just the way we are designing this is track-wise control, how the model we use. And I want to show you this architecture is conformed to that reference model. I highlight the selection of each aspect to interacts to create my track-wise MPC architecture. I can do that track-wise in milliseconds because I have FPGA implementation. Okay, those are defines the observations, the states, and optimize the type, the objectives, etc., and the control. And this, I want to see that some of the information model, that's the next step, right? I'm looking into like 15746. It's like a PLC model, but it's more specific. So, and also, we develop AM data metadata model. So this, I create a data schema on top of this schema. Then with this schema to define all the institute data I collected, all the metadata available, I can do predictive models. Okay, that's it. So just my case. Okay, so it's kind of premature. But I think it's interesting. I cannot, at least it's a testimony. I think this universal SMRM is helpful, and the workflow is, helpful. That's, I will using this to in the future for most of my research problem to identify topics and to find a solution. This is what I feel, this workflow helps a lot to reuse existing standards or ontology or semantic models.
That was a good last sentence. Thank you. Thank you very much, Jianlu, for that presentation.